not so very easy. First of all, we need three things. First one is chiral carbon or molecule. Second one, plane of symmetry. Finally, center of symmetry. If we have these two, if yes, then optically inactive. If we have this, then optically active. If we have this or also this, then it is optically inactive. So first thing, if one yes, but two also yes, then optically inactive. If one yes, two no, three yes, it's optically active, because we don't really care about center of symmetry. We only care about plane of symmetry. If plane of symmetry and center of symmetry both exist, then it means optically inactive. We know that because plane of symmetry exists, then it's obviously optically inactive. That's all. We don't really need center of symmetry, but let's also do that. First one, this molecule. We need to consider steric hindrances in this one. First one, we have C. There are two double bonds and then a H and a CH3, and there is a H and a CH3. First of all, this one is sp2 hybridized. This one is sp2 hybridized, but this guy here is sp hybridized. sp2 and sp2. Let's take this guy px, py, pz. Since it's sp2 hybridized, we shall consider this as px and py, which leaves us with pz orbital. Three orbitals, right, for p. Px, py, and pz. Px and py are involved in hybridization with s orbital for these three sigma bonds. This is sigma, this is sigma, and this is sigma. These three sigma bonds, if we consider s and these two, px and py, that leaves us with pz for this pi bond. See, pz orbital, if the pz orbital is like this, let's assume pz is like this, then this carbon's pz should also be like this. Only then they can form a pi bond, which leaves us with px and py. Px, py. Px and py will be involved in sigma bonds with these two guys. Okay, since this is sp hybridized orbital, which means we will have one s and one px or py, anything that will be involved in the sigma bond formation, and the rest px and py will be involved in pi bond formation. But we don't care about this guy, we care about this guy. This guy is also sp2 hybridized, and pz has to be in this orientation for this carbon, second carbon. Let's assume this is 1, this is 2, and this is 3. We don't care about these two carbon atoms right now. 1, 2, and 3. Third carbon should also have pz in this orientation, which leaves us with px and py in these two orientations. So this guy can form sp2 hybridization and have HCH3 and the sigma bond here, using that those hybridized orbitals, which leaves us with pz orbital, and this guy can form this pi bond. But this guy is also having a pi bond along the x-axis or y-axis. We don't know which one per se. But if we draw the geometry, I mean three-dimensionally, it will look like this. See, this is vertical and this is horizontal. If we draw the plane, then this is how it is. Can you see the difference? Plane difference. This bond, this pi bond, this pi bond is horizontal, this pi bond will be vertical due to this carbon atom, because of this carbon atom. Okay. Since there are two, this is one, then this is two. 1, 2. We have 2 pi bonds. This is the first information we need. If there are 2 pi bonds, then automatically we have to imagine that the 2 pi bonds are in perpendicular planes. This is important. This is always what happens when 2 pi bonds are involved in a series due to this carbon's hybridization, because this is sp hybridized and these two are sp2 hybridized. If this guy is also sp2 hybridized, then we won't have this 2 pi bonds first place. Okay. Next one, we have this in the horizontal plane and this in the vertical plane. This is where the trick happens. Okay? This guy is also having a H and a CH3, and this guy is also having a H and a CH3, which means this is horizontally placed, so the H will go that way into the plane, and the CH3 will come this side. Then this guy is vertical, which means the hydrogen will go that way towards the top, and the CH3 will go down way towards the bottom, but not into the plane or away from the plane. But this guy, H goes into the plane, and CH3 comes out of the plane. So C, H, CH3, double bond C, double bond C, and C and CH3. This is how this molecule is actually present in real life. Okay, now anyone has any chiral carbon? No, everyone is more than sp3, because the sp2, sp2. For carbon to be chiral, it should be in the sp3 hybridization, so that all the 4 valencies or can be satisfied by different molecules. But these guys all are sp2 and sp hybridized, so no chiral carbon. No chiral carbon. First condition is not met. Chiral carbon, no. For first one. Plane of symmetry and center of symmetry. Let's check plane of symmetry. Okay, let's check plane of symmetry. Plane of symmetry. How to do that is we have to cut the molecule in any plane. First one is horizontal plane. Second one will be vertical plane. Horizontally, if we cut this guy, then we will cut these carbons into half. I'll draw it here. Let's take this as a carbon. This is another carbon. This is another carbon. And over there we have a hydrogen. And over here we have a CH3 molecule. This is CH3. Let's say this is CH3. It's star CH3. And here we have hydrogen, and here we have a star. If we cut it horizontally, we will cut these guys. We will cut these guys into half. These guys, since they are in this plane, they will also get cut into half. These guys, since they are not in this horizontal plane but in the vertical plane, they will be as such, one above and one below. CH3 will be below and the hydrogen will be above the plane. Okay. Now let's see what happens when it is cut in the horizontal plane. We will have something like this. And below we will have something like this. We will also have a part of the star here. And then we will have this in remaining part of the star here. And the remaining half of the hydrogen, this remaining half of the star, with this won't be bonded with this guy. But there is a partial bond, and there's a partial bond here. So, because the bond gets broken when we cut it into half. But this guy, the bond is not broken, but then this guy, the bond is not broken. You see, are these two mirror images? They are not mirror images. images. In the horizontal plane, there is no symmetry. If it is symmetrical, they will be mirror images. They are not mirror images, then they are not symmetrical, which means no plane of symmetry. Finished. If they don't have a plane of symmetry, then they are optically active. Simple. Let's check center of symmetry now. Let's take a single point and cut the molecule in any direction. We don't care what direction. And I take the same center, this center, and I cut in the same direction, horizontal direction, and we will again have no symmetry because the same result will be coming to us. Upper side we will have this hydrogen, lower side we will have this CH3, the methyl group, and the hydrogen. We will have two different groups on either side of the cut, which means we don't have a center of symmetry. That is, we have to look from the center. From the center, we are cutting this molecule into two, and we are seeing if both the sides we have the same thing. If we have the same thing, then there is symmetry. But here there is a methyl group, and here there is a hydrogen atom group. We don't have symmetry, which means no center of symmetry. We don't really care about this. So let it be. That is why. See now, we didn't have a chiral carbon or a molecule, but we did have no plane of symmetry. Plane of symmetry should be not there, should not be there. And center of symmetry should also be not there, but we don't really care about it. No plane of symmetry. So yes, this is optically active. First one is right. First one is optically active. Let's talk about second one. What did we have? Okay, Cl towards us and we are away from us. We are here. Do we have a chiral carbon here? How to check for chiral carbon? Okay, let's talk about these two carbons, because in these two carbons, the one atom is different. You see this pair and this here. So we have two carbons which can be asymmetrical, but let's cut this guy into two. You see this carbon. One is bonded with bromine, the other one is bonded with a C, and here the other one is bonded with another C. And this guy has some bond here, and this guy has some bond here, and it is similar. So no chirality. Even for this carbon, you see we have one fluorine here and two carbons here, and hydrogen. There will be hydrogen, of course, for both sides. Carbon, hydrogen, chlorine, and we have the same groups. Carbon with H. The same bonds are present. So this guy is not. This guy is also not chiral, and this guy is also not chiral. So we don't have any chirality. But let's go to plane of symmetry. So we should not have any plane of symmetry. Even for this one, you see, when we cut this guy, yeah, we cut this one in the horizontal plane. What if we cut it in the vertical plane? If we cut it to the vertical plane, then we will have one full methyl group towards us and one full hydrogen atom away from us, and we will have half hydrogen and half hydrogen, half methyl and half methyl. Again, it's the same thing. Same thing is happening again. But this time we will have the complete molecules here and the cut molecules here. So again, no symmetry even in the vertical plane. So vertical plane, horizontal plane. In both these planes, this molecule did not have any plane of symmetry. Let's check about this guy. If this guy having any plane of symmetry in any plane. When we cut this into this half, we have half of chlorine. Let's have this as chlorine, okay? And this is bromine. Let's have this as bromine. And we have not like this. Okay, now it's clear. When we cut this into this half, we have this. And another half. Both are identical, both are symmetrical. Plane of symmetry is crescent. Plane of symmetry crescent. No further ado, this guy is not optically active. Second one, not optically active. Answer ends here actually because we have only one option that does not include the second one, and that is the third option, I think. So that will be the answer automatically. But if you want to do the rest of the things, we can also do those. Third one, bromine. You see, this is biphenyl. Biphenyl or diphenyl, anything you may call it. Whenever diphenyl is present, let's clear this board. We need this board. Whenever we have diphenyl, this is a benzene ring. This is another benzene ring. When these two benzene rings are just connected, this is a biphenyl. When this is present as such, this is a sigma bond. Whenever sigma bond is present, either side, the molecules on either side are free to rotate about its own axis. This guy can rotate about its own axis freely, and this guy can rotate about its own axis freely, either clockwise or anti-clockwise. We don't consider that. When these guys can rotate about their own axis freely, then there is no geometrical isomerism. No geometrical isomerism, because we may have this in the horizontal position and this in the vertical position at a point of time, but it can change its own orientation freely because this is a sigma bond and there is no energy required to rotate these things. So we may have at one point this in the vertical plane and this in the horizontal plane, and another point of time this in the horizontal plane and this in the vertical plane. So we don't have any geometrical isomerism. Cis and trans, no, it is not at all present when this is a sigma bond. These guys were not sigma bonds, these guys were pi bonds. So there is an energy required to rotate this guy. You see, this guy can also be present the same orientation, but it does not happen. It didn't happen because of these sp hybrid. What if we have had another carbon here, and that guy was having H and CH. This guy can have its bond broken, and this guy can become a carbocation, and this guy can become a carbanion, getting this bond broken, and this will be a sigma bond, and now it can rotate, and after rotation it can again use that energy and form another bond. So rotation can happen with the expenditure of energy when there is a pi bond involved. When there are 4 carbons here like this, there is another scenario. What will happen is carbon, 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 carbon. This and this will be similar, and this will be in the another plane. These two guys will be vertical, and this guy will be in the horizontal position, or these two guys can be in the horizontal position, and this guy can be in the vertical position. I am saying about the pi bond. The pi bond can be horizontal here, horizontal here. If 1, 2, and 3, we are naming these pi bonds as 1, 2, and 3. If 1 is horizontal, then 3 should also be horizontal. If 1 is vertical, then 3 should also be vertical. This is what happened. I don't have to explain this, but this is how it is. You have to know this by now. And now, if these guys both these guys are in the same plane, then this H and this is H and this is CH3 and this is CH3. We will have plane of symmetry. We will also have center of symmetry. So this guy cannot be optically active. When only 3 carbons were present, I mean involved with the pi bond formation. This guy here we have 4 carbons involved in the pi bond formation. Here only 3 were present. When 4 are present, then symmetry comes in. But when 3 were present, there was no symmetry. So when 4 guys are present, no, this guy is not optically active because we have plane of symmetry and center of symmetry both. Let's come here now. This guy has plane of symmetry. Yes, of course, this guy has plane of symmetry. If we have a center, let's talk about this as the center. If this is the center, then towards the left and towards the right. Towards the left, I have half a Cl, half a bromine, and towards the right, I have again half a Cl and half a bromine in the same orientation. So this guy has no center of symmetry. But if I check it from towards this direction, towards this side, I have left side and right side, half Cl, half Cl, but here I have half pair and half pair. So this is not a center of symmetry. We don't have a center of symmetry in this direction. But when we go from us to inside the board, then we will have a center of symmetry. When it is in this plane, when it is in the vertical plane, there is no center of symmetry. But when it is in the horizontal plane, then there is a center of symmetry. So anyway, we don't care about COS, we only care about POS. This guy has no plane of symmetry. What did we talk about? I'm sorry. We are talking about biphenyl, right? O-ambiguous. Biphenyl. Let's come to biphenyl. So rotation, when these guys can rotate about their own axis freely without any energy expenditure, then this guy has no geometrical isomerism whatsoever. If they ask what are the possible geometrical isomers present for this two, it's zero, none. Now let's talk about additions, ortho additions. We may also have meta and para additions. Let's have this as A and this as A, and this as B and this as B. In our case, these were chlorine and bromine. A was chlorine, B was bromine. Both of these guys are in the same plane. If these two were the same plane, then these guys will also be the same plane and will facing each other, and these guys will be facing each other, which means repulsion. There will be repulsion. Repulsion. We don't want any repulsion. What can happen? This is a sigma bond. It can rotate about its own axis freely. So what happens is we have this in the horizontal plane and this in the vertical plane, or vice versa, anything can happen. This is in the vertical plane. And this is in the horizontal plane. Sorry, vertical plane. This is horizontal, this is vertical. A, B, A, B. This is vertical, this is horizontal. We can see clearly that this is vertical. Sorry, this is horizontal and this is okay. Chiral carbon. No chiral carbon. Everybody is sp2 hybridized, so no chiral carbon. We don't care about chiral carbon, we care about plane of symmetry. Let's cut it in the horizontal plane. When we cut it in the horizontal plane, we cut this guy into two layers, one above and one below, and this guy into two halves, one upper and one lower. So we will have half a benzene, half a plane of benzene, and we will have half A, half B, everything, one above and one below. And here we will have completely one A and completely one B below, one A above and one B below. The A and B are not cut for this benzene, but the A and B are cut into half in this benzene. This is in the horizontal plane. When we cut it in the horizontal plane, no plane of symmetry. The same is going to happen in the vertical plane. So when we cut it in the vertical plane, no plane of symmetry. It's finished. There is no plane of symmetry, then it is optically active. This guy is optically active. This is easy. This is a chiral carbon, and this is a chiral carbon. When we have two chiral carbons, you see, another general rule of thumb is if one asymmetric carbon is present, only one asymmetric carbon is present, then it is optically active 100%. We don't have to talk about anything else because it will never ever have a plane of symmetry because this is sp3 hybridized. When it is sp3 hybridized, this will be the carbon and this will be one bond, this will be another, this will be another, and this will be. We cannot have a plane of symmetry at all when this is sp3 happens. Let's go with this plane. Sorry. If we go with this plane, then we will have what? Towards the left side, we will have B, and towards the right side, we will have C and D. If we go with this plane, then what will happen? We will have D there and B and C here, and A also towards that side. So we cannot have plane of symmetry at all whenever we have a single parallel carbon. When we have two parallel carbons, that is another scenario. We can have a plane of symmetry. Let's check this. When we go with horizontal plane, one above and one below, we have H, OH, H, OH, similar. We may think this is symmetrical, but you see this group here is COOH, but this group here is COOCH3. So different. When we cut this into the horizontal plane, we don't have a plane of symmetry. Very nice. Why not? When we cut it in the vertical plane, again, we don't have a plane of symmetry because we are cutting COOCH3 into half, and here we are cutting COOH into half. So again, we don't have any plane of symmetry. In both the planes, we don't have plane of symmetry. If we don't have a plane of symmetry in any plane, then that is optically active. If we have a plane of symmetry even in a single plane, then it will not be optically active. Here we don't have plane of symmetry in both the planes, so this guy is also optically active. Let's talk about another molecule who looks exactly like this guy. COOH, COOH. Sorry about this. OH, H, OH, H. Now let's go to the horizontal plane. If we do this horizontal plane, we have H, 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 COOH, COOH, exactly similar. So there is a plane of symmetry. A plane of symmetry is present. When we cut it in the vertical plane, then again we have plane of symmetry because we are cutting COOH into half, COOH into half, and we have H, H left side and OH, OH on the left and right side. It's nearly similar. Even though if we see H, H and OH, OH, towards the left we have hydrogen, towards the right we have OH, so it's not symmetrical. Okay, let it be, but we have a plane of symmetry in the horizontal position. I think we made a mistake with that one too. Yeah, when we go with the vertical plane, we don't have a plane of symmetry. I mean, yeah, we don't have a plane of symmetry because we have H on the left and OH on the right. So we didn't see that. But yeah, with these two, we don't have a plane of symmetry. But it is added, it's confirmed that we don't have a plane of symmetry. But here, we don't have a plane of symmetry in the vertical position. Vertical, no plane of symmetry. But in the horizontal, we have a plane of symmetry. Because we have a plane of symmetry, at least in the horizontal plane, this guy is optically inactive. Okay. Finally, n-hexane. Nothing happening. No chirality anywhere. Simply finished. Plane of symmetry, of course, no plane of symmetry because this is a chain molecule. There is nothing special about it. This guy is not in. This guy doesn't have any branch even. This is a simple n-hexane, normal hexane, straight chain, linear. For a linear chain compound, all we need to have is a chiral carbon. Since this guy has no chiral carbon, this guy can't be optically active. Simply finished. These guys are all special cases. This is a cyclic compound. This is a biphenyl. This guy had two chiral carbons. This guy has 5 bonds. Hybridized. We have different hybridization. We have different planes. So these guys were all special cases, but this guy is not a special case. This guy is a simple case. We have a chiral carbon, then it should be optically active. Since this guy does not have that, this guy can't be optically active. So this is also not. So we have 1, 3, and 4. Only these guys are optically active. 2 and 5 are not optically active. 1 and 1, 3, and 4. That was in the third option, I guess. So that must be the answer. It took nearly 15 or 20 minutes to explain this, I guess, but how to do it in 1 minute? Simple. 2 pi bonds. 2 pi bonds means one has to be horizontal, one has to be vertical. This is vertical and this is horizontal. Let's imagine like that. This will simply furnish that H is away from us and CH3 is towards us. These H's towards the top, this CH3 is towards the bottom. Simply finished, no plane of symmetry, ergo optically active. This one, plane of symmetry. For E, if we draw it straight, then this guy will have no, they will have a plane of symmetry, so ergo this guy can be. This is the biphenyl. Biphenyl means one will be in the horizontal position and the other will be in the vertical position to avoid this repulsion between these guys, between chlorine and between chlorine. So then we will have no plane of symmetry. So then this guy can be optically active. This guy, simple, one horizontal plane, and we can compare these two. If it is the same, then it will be optically active. If it is different, then of course it will be optically active. Simple. Nearly 30 seconds, maybe. That's what